In this video, we're going to talk about linear regression when we have categorical independent variables. And we're going to use data file ButlerHighway. So categorical variables are variables that take nominal values rather than numerical values. For example, season. You cannot associate numerical values to different seasons of a year, like spring, summer, fall, and winter. They don't carry numerical values. They're just labels, right? So categorical independent variables. And we have a lot of cases. We have a lot of variables that are important in business, but they're categorical. And you can't simply put labels. You can't simply put nominal values in regression analysis tool pack. Like in regression tool, it's going to give you error. Regression analysis is a statistical analysis. It actually is it deals with numbers, and you can't simply use text. All right, so it's a numerical approach, and in order to be able to use categorical variables in regression, you need to first convert them to numerical values and then use them into your regression analysis. All right. So in the next example, we have the same example, Butler Trucking Companies, but now we have another variable, a categorical variable, and that would be the notion of rush hours, taking the highway during the rush hour. And that's the answer to that. This variable is it's going to take either yes or no. So it's definitely a categorical variables. Yes, I took the highway, or no, I did not take the highway during the rush hour, right? So that's a categorical variable, taking the highway during the rush hour. If we run the regression without taking rush hour, without actually considering this factor, and get the equation, what happens if we draw the residual, the frequency of residuals for cases where the rush hour driving, the answer to the rush hour is yes, versus the frequency distribution of residuals for when the basically the answer to the rush hour driving is no, did not include the highway during the rush hour. If we draw the frequency, by definition, residuals should have symmetrical distribution around a mean of 0, right? So symmetrical distribution around the mean of 0. That's what we know. Residuals should follow a normal distribution with a mean of 0. But that's not the case here in this example. Residuals are not. Residuals are actually skewed. For the cases where the driver took the highway during the rush hour, we see that it's skewed to the left side. Most residuals are taking positive values, whereas when the driver did not take the highway during the rush hour, residuals are now negative. It's skewed to the right side. Most values are negative. So positive residual means residual is y minus y hat. Positive residual means that y is less than y hat. So the model, the estimated model, is actually underestimating the travel time. So if you just include both of them and come up with one overall regression that does not take into consideration the rush hour driving, for those cases, for those travels that include highway, taking highway during the rush hour, the model is underestimating the time, and it overestimates the time for the assignments that did not include highway during the rush hour. So that's actually a problem, right? That means that factor actually is making some effect on the travel time. So therefore, we should include it. How do we include it? By converting the yes and no's to 0 and 1. And we call that variable a dummy variable. So now, instead of yes and no for highway, so whenever you see 0, this means that the driver did not take the highway during the rush hour. Whenever you see 1, it means that the driver took the highway during the rush hour. And this column is called a dummy variable. I'm just to show you, I'm gonna filter the table, and highway here, as you can see, it's either 0 or 1. 0 when the driver did not take the highway, 1 when the driver took the highway during the rush hour, right? And if we include this now into the regression, so in this example, in the Butler example, we've been dealing with this multiple times now. We are predicting the time. So the time, travel time, is what we want to predict. And we predicted the time based on miles and deliveries. And now we want to add a dummy variable. So now this one is not yes or no. This one is not, is actually a numerical variable, a dummy variable that allows us to incorporate the categorical variable of yes and no for taking the highway during the rush hour into our regression model. So this is really how we do this, by converting the text, the categorical variable, into zeros and ones. All right. And this one, this specific examples had only 2 levels, yes and no, right? So when you have 2 levels, when your categorical variable has 2 levels, you just need 1 independent variable. So we will talk about more complex cases when your categorical variable includes more than 2 levels. I'm going to talk about that after this example. But let's get the equation and interpret the equation, and then continue with more complex cases, right? So I'm going to find the equation. I don't see the data analysis, so I'm going to refresh. File, options, add-ins, go. I do have the analysis tool pack here, so I'm going to check it off, and I'm going to add it again. Options, add-ins, go, analysis tool pack. Okay. And now I go back to data tab, and it added it now. So data analysis, regression. So we want to predict the time based on miles, deliveries, and highway, all the way to the end of the table. All the way to the end of the table. So column E is my Y range, column B, C, and D are my X range. I have labels, and then I'm just gonna put the output in H1, and residual plots, yes, It's a multiple regression and I have one categorical variable. So I just check the residual plots just to check the necessary conditions for residual. All right. And okay. All right. So now the equation is as follows. I just need to record the coefficients. Travel time equals the intercept minus 0.33 plus the coefficient for miles times miles plus the coefficient for deliveries times deliveries plus the coefficient for highway times highway. So this is the equation. And when we check the p-values, I mean, we can just check the residual plots. The residual plots are all beautiful. They all show symmetric distributions around mean of 0, and we have more or less constant variance as we go from left to right in either of these graphs, residual plots. All right, so the necessary conditions are satisfied. You can also check for multicollinearity. For highway, when you have categorical variable, it's usually better to remove highway and check the p-values again. But since p-value for highway is significant and all other p-values, both p-values for miles and deliveries, they both are less than 5%, you don't really need to do that. But in general, when you are a dummy variable, the correlation that you get is not really representative of the actual correlation between the dummy variable and not dummy variables. So it's better to remove it and check the p-values rather than just by taking the correlation. But it's absolutely fine if you choose to do it using a correlation. If you check multicollinearity, it's better to do it manually by removing it physically from the regression and running the regression again without the dummy variables. But again, it's okay for the sake of our course. It's okay to check the correlation. Check multicollinearity by just the correlation. And for correlation, you need to check it only for the independent variables, miles, deliveries, and highway, all the way to the end of the table, grouped by column, and right below here, M2. So column B, C, and D, grouped by columns, put it in M2. Input range contains non-numeric, so labels in the first row, okay. So these three, I have three independent variables, and I will have three pairs of basically three couples, miles and deliveries, miles and highway, highway and deliveries. They're all less than 0.7, so multicollinearity does not exist. That's okay. Multicollinearity does not exist, and we have the necessary conditions are satisfied. We can go ahead and check the p-values. All the p-values are less than 5%, so all factors are significant. All variables are significant. which means that they have, all of them have significant relationships with the travel time. All of them significantly contribute to the travel time. Distance, deliveries, number of deliveries, and whether the driver takes highway during the rush hour. So they all are significant. They significantly influence the travel time, all right? Why? Because their p-value is, their p-value are less than 5%. I'm just checking it for independent variable. All right. One last thing before we move on, before we go back to the slide, would be the interpretation of the equation and the coefficient in the equation. So we talked about these ones. We talked about the intercept. Intercept, this is the average travel time if miles 0, if there's no miles, there's no delivery, and there's no highway. So no highway during the rush hour, no deliveries, no mileage. The average time would be 0.33. So that's the interpretation of y-intercept. The coefficient for miles, 0.067, which is equivalent to 4 minutes. So this is the time that each additional mile, assuming everything else is the same, that would take. I'm going to insert a few cells here. So 0.067, this is the time that, the extra time that each additional mile takes. This is very important. Assuming everything else constant, which means deliveries are the same, the number of deliveries stay the same, and then highway selection also remains the same. The driver either goes or not. We don't change this one. The only thing that changes is mile. The distance goes up by 1 mile, and then the time goes up by almost 4 minutes. The time that each additional mile takes, assuming everything else remains the same. The hour, actually, so our times here are in hours. So 0.067 hours or 4 minutes is the time that each additional mile of travel takes, assuming number of deliveries and the highway choice remains the same. And then the next one, 0.67. I'm just trying to, these are what we have already talked about, but just to make sure that I just want to get to the highway one, the time that each, so for this one, the delivery is the time that each delivery takes, assuming everything else constant. All right, assuming everything else remains constant, the time that each additional delivery takes is 0.67 hours or almost 40 minutes or 45 minutes, all right? The next one, highway. Highway now, highway can be either 0 or 1. So if I put 0 here in highway, if I plug in 0 here, this is going to go away. The time is going to be minus 0.33 plus the rest of the equation. But if highway takes 1, the equation is going to be the same thing plus 0.998. So what happens with the highway is that if highway is 0, the intercept for the equation is going to be minus 0.33. But if highway is 1, the miles and deliveries will still have the same effect, but the intercept is going to go up by 0.998 hours, which basically means that if the highway is 1, the dummy variable for highway is 1, this is the additional time, the time that takes, the time that taking the highway during the rush hour takes. Again, assuming everything else constant. So now what this dummy variable actually is doing for us, it's creating two parallel lines for miles and deliveries, one with an intercept of 0.33 minus 0.33, and another one with the intercept of minus 0.33 plus 0.998. One of these lines, two parallel lines, only the intercept is different. One of them is for when the highway is 0, the other one is for when the highway, the dummy variable highway is equal to 1, all right? And the coefficient for highway is the time. So almost 1 hour longer would be a travel if it involves taking the highway during the rush hour. So that's the interpretation of this coefficient, all right? So this is really important, being able to interpret the highway. And then moving back here into the slides, and I just want to mention one more point here. Please go ahead and read these slides. One more point here, when we have more complex categories. So in the example that we just did, the highway, we had the categorical variable taking the highway during the rush hour only took 2 levels, yes or no. But what if we have more than that? What if we have a dummy variable that takes more than that? For example, if you take season, it takes 4 levels. If you take educational level, it may take, depending on how you're defining the educational level, it can take multiple levels. For example, high school, college, some college, university, graduate studies, and so on and so forth, right? So it doesn't have to be only 2 levels. It can take like any number, basically, any number of levels. In general, if a categorical variable has k levels, we can convert this, we can convert it to numerical variables using k minus 1 dummy variables, k minus 1 dummy variable. So if you have 2 levels, yes and no, male and female, you just need 2 minus 1 dummy variable. If you have 3, A, B, and C, for example, regions A and B and C, you need 3 minus 1, 2 dummy variables. But how do we do that? What does it mean? So you just need to define 1 dummy variable for A, 1 dummy variable for B, and that's it. So dummy variable for A would be 1 if sales region is B and 0 otherwise. So if the sales region is A or C, actually I said A and B, that doesn't really matter. You just pick two of the three as your basically dummy variable to identify your dummy variables, and the other one does not need a dummy variable. Similar to taking the highway. Taking the highway, we said that one is 1, and then the other one is 0. Now, if you have 3 levels, you need to define it for 2 of them. You just pick 2. Here we picked B and C, and then A will be automatically defined, because if it's not, if x1 takes 0 and x2 takes 0, by definition, it's going to be identified as A, because it's not B and it's not C. The only choice that is left would be A. So now you don't really need to define another one for A. So if you just need, if you have 3 levels, you need 2 dummy variables, all right? So before, males and females, if you define 1 for females, 1 females, therefore 0 will be male, all right? So you just need 1 variable if you have 2 dependent, 2 levels in your, for your categorical variable. If you have K, you need K minus 1. You just define it this way, and then the last one, whatever it is, it's gonna be taken care of by itself. So, and now the interpretation of this would be as follows. This is very important. Beta 0 plus beta 1 x1 plus beta 2 x2. I said in the highway example that we just did, the coefficient for highway only impacted the y-intercept. This is, again, exactly the same. So we will have, depending on when x1 and x2 are 0, or 1, only one of them can be 1, or both of them should be 0, all right? So we have 3 cases. It's either A, B, or C. If it's A, that means x1 and x2, both of them are going to be 0. If we're dealing with region C, this is how we defined it, right? So we have B associated with x1, C associated with x2, and then when both of them are 0, it's going to be region A. So when we're dealing with region A, x1 and x2, both of them are going to be 0. So if you put 0, 0 here, it's going to be your y, estimated value of y is going to be beta 0. So that's the intercept for region A, the one that you did not use to define your dummy variable. When you define it for region C, C would be when x2 is 1 and x1 is 0. So your estimated y would be beta 0 plus, it's actually expected y would be beta 0 plus beta 2. So now the beta 2 is the way we actually interpret beta 2. Beta 2 is the difference between the value of y for C compared to A. So beta x2 is the difference between C and A. And similarly, beta 1 is going to be the expected difference for y. I mean, the expected difference for y when you're comparing B versus A, right? So this is really how you should be able to interpret the result of categorical independent variables. So just remember, if you have K variables, K levels for categorical variables, you need K minus 1 dummy variable. And you just need to define it this way. 1, if you're dealing with level A, if the categorical variable is equal to level, one of these level, 0 otherwise. And you just define it for K minus 1 level. And the last level is going to be taken care of by itself. So that's one thing. The second thing is the interpretation of the result. The coefficient for each one of these dummy variables is going to be the difference in y for the level that you identified it with, your actually dummy variable with the one that you did not include in your I mean the definition of your dummy variables for that categorical variable.